Good evening to all of you.
Good evening, sir.
Good evening, sir.
Okay, so is there any query related to the previous discussion? Okay, so I have shared my screen. I hope it is visible to you.
Yes, sir.
Okay. So in the previous lecture, we derived formula for area of laser footprint. Okay. So we discussed that if let's say this is the laser transmitter aperture through which the laser source emanates the laser beam. Okay. And it has a, let's say if this is the diameter transmitter is dt, then the beam that is emanates from the laser source, that is from aperture dt, travels in a straight line, and finally it hit the target point P. Okay, so it's not confined to the, it's not very pointed. Okay, the system is designed like that. It should be pointed, or we can say it should be highly collimated. But due to some restrictions, some limitations of the internal instrument, this internal electronics, as well as the diffraction in the medium, around point P, the energy that is hitting that around point P, the surface that is hit by the energy that is having a specific area, we'll call it this, let's say this is footprint, so diameter of laser footprint df. Okay, and df is always greater than dt in case of this real medium. If we say in case of ideal medium there is no diffraction, then the footprint is equal to, diameter footprint is equal to dt, that is exactly equal to the diameter of transmitter aperture. And we have calculated df is equal to dt plus 2h tan gamma by 2. Okay, where this gamma is the angular deviation. Okay, how much angular dispersion occurred when that laser beam progresses towards target point P from laser source. Okay, so this here we can see that the diameter of laser footprint, it has its dependency on transmitter diameter dt, how far away that laser source, this target point P from the laser source, and what is angle, this gamma. Okay, and also told that the due to the diffraction, this gamma is calculated experimentally 2.44 lambda by d. Okay, it's a dt, transmitter diameter. Okay, now by using these two equations, let's say the first and second, by using these two equations as a fundamental concepts, okay, how we can justify that why we do not select laser in radio band. Who will tell me? At very high frequency, at very high wavelength, it is eye safe.
Sir, at radio waves, sir, actually has large wavelengths. Those who have radiations have large wavelength, they have less amount of energy. So for the remote sensing purpose, uh, for sensing purpose, sensor has to see large area. That is
No,
why we select.
you mean to say that you are correlating the laser pulse energy within the laser pulse that is generated with and its relation with the wavelength.
Yes, sir.
Okay, fine. Like when we see energy within a photon, so that is SC by lambda. So obviously, if the wavelength is large, then this energy will decrease. It is fine. But by using equation 1 and 2 and laser selection in radio band, can it be justified on the basis of only equation 1 and 2? Why we select laser only in infrared band or visible spectrum? Why not at wavelength which are higher than these spectrums? Why not in microwave, that is in radio band?
Sir, atmospheric window.
सर गामा की वैल्यू बहुत ज्यादा आ जाएगी सर.
Yes, who is there? Actually, किसने रिस्पॉन्स दिया गामा के टर्म्स में?
सर शुभम.
Yeah, good. सी एटमॉस्फेरिक विंडो का कॉन्सेप्ट नहीं है ना यहाँ पे. इट्स एक्टिव रिमोट सेंसिंग टेक्निक एंड the imaging is done only at 1 kilometer height from the ground. I have already summarized that. Through a different platform, we do the laser scanning, ground based, vehicle based, and airborne, or UAV based. Okay. And all these platforms, if you see that the target distance from the laser source is around 1 kilometer, maximum 1 kilometer in airborne we have. While in TLS, it is ground based, it is only few meters. Okay, in mobile LiDAR, again, we have a 300-meter maximum coverage. UAV LiDAR, we have kind of like 100 to 200-meter coverage, 300-meter coverage. It all depends, I think, at what altitude you are flying the UAV. Okay, so there is the signal energy propagation within a kilometer, not more than that. Atmospheric window is a different concept that is related with the remote sensing, where energy comes from sun, travel through the medium, interact with the target, return back, and again sense by the detector satellite on board. And those detectors are, I mean, 300, 400 kilometer altitude. Okay. So anyway, I think it's an open discussion, so you can think from different perspective. It's good part. So see, in equation 2, if you see that the lambda, when we select very small, like lambda in case of visible, in the visible spectrum, we have red, green, and blue. It is comparatively equal to lambda in NIR. Okay. But these are very less when we select lambda in radio band. Okay. So lambda in radio band is very high. And by using the formula second, if you can see, this diffraction deviation will increase. So when gamma will increase, what will happen? This second component value will increase. And that will finally lead to increase in size of laser footprint. And it goes in kilometer. So when laser footprint, like we are interested in point P, and I told that this it should be desirable that DF tends to 0, so that it is a point, and at one particular point all energy is hitting. But it doesn't happen around point P1 in a certain area. We call it footprint. Energy strike. Okay, and we have a return response in terms of reflected energy. But by increasing this wavelength, okay, when it enters in the radio band, gamma increases and DF increases, and DF value will go in kilometer. And in that case, it's very inaccurate measurement, even in X, Y, and Z as well. Okay, this is the reason why we do not select it in radio band. We only confine in NIR as well as visible spectrum for bathymetric LiDAR. Okay, why we select green laser in case of bathymetric application for water body mapping? Who will tell me? For the water body mapping, why we select laser in green band? Sunil Kumar, could you please unmute?
Yes, sir.
Question is clear to you?
Sir, just a
Question,
bit.
क्या चीज?
Sir, just a bit join क्यों sir? Please repeat question again.
Question ये है कि for water body mapping, why we select laser beam in green band? Alok Kumar,
यस सर। सर
बताइए।
ग्रीन बैंड में इसलिए करते हैं क्योंकि अगर हम एनआईआर में वाटर बॉडी का करेंगे स्कैनिंग तो सर वाटर ऑब्जॉर्प्शन वहां पे एनर्जी का ऑब्जॉर्प्शन हो जाएगा और रिफ्लेक्टेंस नहीं मिलेगा हमें सेंसर पे, जिसकी वजह से ट्रिगर्ड और स्टॉप ट्रिगर टाइम वाला जो सिग्नल है वो नहीं हो पाएगा। तो फिर हम और
Yes, good.
फाइनली सर कोऑर्डिनेट हम डिटरमाइन नहीं कर पाएंगे उसका।
Yes. So this is the region, correct region. Thanks. And see, if you see the spectral signature of water, okay. So on the independent axis, there is a wavelength in micrometer. Then on the dependent, we have a reflectance. And reflectance is a constant, varies from 0 to 1. So it is a ratio between a reflected energy and incident energy. When you see in case of water, it is from 0.4 to 0.7 and peak we have at 0.6. That is green. So within the green band, we'll get the peak. Okay. So highest reflectance within visible spectrum is obtained from the water in green band. This is the reason why we select lambda green for water mapping, water body 3D mapping. Okay. Now we'll move to the next discussion. And we have been discussing about characteristic of a LiDAR system. Okay. And its relationship with the Earth surface object, which are being 3D imagined.
सर 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 अभी आपने जो ये बताया ना ग्रीन वाला रीजन थोड़ा सा एक बार और बता दीजिएगा।
Okay. Fine. So see what happened. Like I start from the basic. Okay.
ओके सर।
From the remote sensing concept. So what happened in the remote sensing? Sun is act as an external energy source, while in LiDAR there is a laser beam. Okay. And if you see that, then this is the curve, and this is the radiated energy from sun with respect to wavelength lambda. Okay. And the highest energy we have within the visible spectrum. So lambda m at which we obtain the highest radiated energy from sun is equal to 0.48 micrometer. Okay, so this energy travels through the medium, and finally, let's say if it strike with the water body, let's say it is striking to the ocean. Okay, so this energy that is m lambda, this is the function of wavelength, as you can see over here. With respect to wavelength, the energy that is coming from sun varies, and this is the variation plot, how it is varying with respect to wavelength. At point A, at the water surface, when this m lambda interact, okay, there is a phenomenon that is incident energy EI. Okay, this is the normal at this point. This is the incident energy EI. This is the function of wavelength as well. Okay, we have a reflected component, transmitted component, and absorbed component. Okay, so this EI is equal to E absorbed plus E reflected plus E transmitted. Okay, if you take the ratio, if you divide the left hand side and right hand side by incident energy component EI, then you have E absorbed EI. With the discussion, I suggest you to make a note as well. Okay, on your notebook, if you want,
Yes, sir,
I suggest you, all of you, to write it. Okay, then absorbed component divided by the incident energy, then again this radiated, this reflected component divided by EI plus E transmitted. Okay, divided by EI, and again it is equal to absorbed. You can use some, let's say, absorbance by symbol sigma. It is wavelength, function of wavelength lambda, because all these parameters are the function of wavelength. Okay, so EI is a function of wavelength, EA is function of wavelength. So it's a absorbance plus we have rho, it's a reflectance. Okay, plus transmittance we have. So you can use some variable beta. Okay. In case of laser scanning, we are only interested in the this reflected component. Fine. When we analyze this equation from the water surface, what happened? The reflected component, see, incident energy is available in all the wavelength. Okay, but due to the internal molecular composition of water, some internal chemical properties of water, this rho lambda that we say now, it is this rho lambda is not equal to 0, you can say, for the wavelength 0.4 less than lambda less than 0.7 micrometer, while for the rest of the wavelength it is nearly equal to 0. Fine. Now, can we plot it graphically? इसका मीनिंग ये है कि जो the reflected energy component है, so the reflected energy component we only get 0.4 to 0.7 micrometer from the water, and at the rest of the wavelength water completely absorb का मीनिंग क्या है कि in that case sigma lambda is close to, you can say, the sigma lambda plus beta lambda, they will be equal to 1 because it is constant, all these equal to 1. So when this reflectance is equal to 0, in that case, these two phenomena by law of conservation of energy, this addition of these two will be equal to 1. And this happens for the wavelength which are outside of 0.4 to 0.7 micrometer bracket. Outside of the visible spectrum, towards higher side of the wavelength, water body completely absorb the energy. Okay. So it can be plotted. We'll call it a spectral signature of water. On this axis, it's a 0 to 1. Why I am writing this 0 to 1? Why the range of reflectance is only 0 to 1? It's a ratio, no? It is a ratio of radiated divided by incident. And just see, incident energy is a complete, it's the highest, and it is divided into 3 parts. So obviously, when you will take the ratio, the values will rise between 0 to 1. And let's say somewhere we have a 0.4 and 0.7. Okay. Only within this around 20%. Okay. So you can see 0.2. It is reflected back. So this rho lambda value will have a value 0.4 to 0.7 micrometer more than 0. While for the rest, it is equal to 0 for higher wavelength. What does this mean? It means you will get a reflected component from the water surface only within the wavelength 0.4 to 0.7 micrometer. Okay. And this will be the shape, and highest you will get at green. Okay. And this return, it means if I plot over here, so this is the reason why in laser scanning, we have an option to select a laser beam, like at which wavelength you want to generate a laser beam. So if, let's say if we have a water body to be mapped. Okay. So in that case, its lambda selection is monochromatic, and the lambda selection is in green band. And this is the reason why we select it. So in green band, laser beam is fired. It can goes, one reflection we'll get from water surface. So in case of water body, this laser beam, one reflected will get from here, and then second will get from the water bed. So I hope it is clear now. Sumit, it was your query, no?
Yes, sir. It is very clear.
Good. Okay. Now we'll see the property of laser beam, and we'll analyze that property in terms of data quality. Okay. So there are certain limitations of internal electronics of LiDAR instrument that we'll see on the basis of parameters. So the laser source which generate the laser beam this is the transmitter, and it generates a laser beam. We are discussing the pulsed laser system. It means a periodic laser pulse is generated and it is continuously fired by the laser source. Okay, so this on the dependent axis is amplitude. Okay, so this is the periodic signal, and we'll define the rate at which this laser pulse are generated. So you can calculate, this will become a time period t. Okay, so it's a periodic signal. It is designated by time period t. It is designated by the a max. We'll call it a peak amplitude. It is designated by the TP, that is pulse width, 50% level. So what is width? This is given by the TP. Okay, so we have a time period of laser pulse. We have a maximum peak amplitude. We have a TP. So using these parameters, you can figure out what is the energy within a laser pulse, what is the power, what is the average power, okay, as well as what is the rate at which this laser beam is generated. So the rate that we'll call a frequency, generally we call a pulse firing rate, is equal to reciprocal of time period, so 1 by t. Now we analyze what is the relationship between the pulse firing rate and flying altitude. Okay. Let's say that is height h. At what height the aircraft is flying. Is there a relationship between these two parameters, or they are independent? Okay, so this part we are going to discuss now. And similarly, we'll have further concepts. And finally, we'll combine all the equations, all the concepts to see how these parameters are selected. Okay, so there will be a trade-off condition which will arise, and we'll see what is the optimal selection. So we'll first start with the relationship between pulse firing rate and flying altitude. So you are already aware about what is PFR, okay, and what is flying altitude. Okay, so this discussion will start with the airborne laser scanning. So should I erase this? Please let me know if you're making a note, then let me know. If you have written it, then I need to erase it. Okay. So at time t1, the first beam is fired. At time t2, second beam is fired. And at time t3, third laser beam is fired. Okay. And obviously, when these beams are fired, then its orientation will change. So that, let's say somewhere for the first beam, this laser footprint, let's say for T1, at time T1, this position is T1, then oriented T2, then this is T3. Okay, now the query is that when the laser pulse T1 is fired, okay, does the laser transmitter fire the next beam before receiving the return from T1? how does this laser receiver identify the return which is coming, that is corresponding to transmitted pulse T1, T2, or T3? We'll call it pulse limitation. So in like starting days when this technology evolved, the sensors which were there in the market, they had a limitation of a single pulse. We'll call it single pulse limitation. So single pulse limitation tells that this transmitter doesn't fire the beam T2 until it receives the return of T1. Okay, it means this when this T1 beam is fired, it hit the point P1 over here. Okay, and it is reflected back. Receiver sends the return of T1, then only beam T2 is fired. So it means ultimately it determines. So first we'll see. Let's say if your aircraft is flying at height h. Okay. Aircraft is flying at height h. So in two-way movement, we can say that two-way, the forward propagation and then backward propagation. To cover this height h in forward and backward direction, how much time is needed for a laser beam? Who will tell me? The total time needed to cover the distance h two times, forward and backward. So let's say if the beam is traveling at a speed of light c, so how much time will be required?
H/c, sir.
That is
H by C.
forward and backward, both direction. That is
It's
2h by c. Fine.
yes, two times.
It's a 2. It means like this is the laser source. Okay. And this is the target T1. Height h. And the energy travels with the speed of light c. Let's say this is the origin O, we can say, and this is point P. So distance. So the distance between origin O and point P is equal to flying altitude height h. Okay. Then time taken to cover, time taken by laser beam from origin O to P is equal to h divided by c. Fine. And now it's two-way, O to P, then back to O, and it travels in a straight line. Same path is traversed in backward direction. So the total time, T total, that will be taken, we also call it time of flight. It's 2 time TOP, and it will be equal to 2h by c. It means when the T1 is fired, okay, and it travels from O to P, then back to O, at least 2h by c time will be needed before firing the T2. Is it clear? If it is not clear, let me know, because now we are building the fundamental. Meaning is that when this T1 is fired, okay, so this pulse T1 will take 2h by c time to travel from O to P and then back to O. And this is the minimum time that will be needed by the transmitter before firing the T2, second pulse. So we can say that this is T minimum time required by laser transmitter to in between the transmission and reception. Okay. Can we determine this? Can we correlate this T minimum with the wavelength? What is wavelength? Wavelength is this time T. Sorry, this time period. This is time period T. Okay. It means the minimum time period. The minimum time period should be equal to 2h by c. Okay. And it can be more than that. If you increase it, it's fine. Like when this T1 is starting from O to P, then back to O at height h, time required 2h by c. Single pulse limitation tells that you can't fire that pulse T2 before receiving the return of T1. So the T1 return after time 2h by c. So after time 2h by c, the next pulse is fired. If you want to fire immediately after 2h by c, then time period T minimum is equal to 2h by c, and this is time period T. Is it clear to all?
Yes, sir.
किसी को डाउट हो तो let me know. Praveen, could you please unmute?
Yes, sir.
बताइए क्या समझा आपने इसमें?
सर जो डिस्कशन हो रहा है मतलब क्लियर तो हो रहा है सर, टीचर इतना डिस्कशन हुआ है सिंगल पर्स लिमिट के लिए।
नहीं तो अभी हमने क्या डिस्कस किया यहाँ पे? क्या
सर
क्या
बेसिकली हम
कॉन्सेप्ट
क्या नाम यहाँ पे
बताओ।
सर बेसिकली हम यहाँ पे आए हुए थोड़ा सा बाहर आए हुए हैं, क्या नाम सर में प्रॉब्लम थी तो चश्मा बनवाने के लिए दिए हैं, उन्हीं की दुकान पे बैठे हैं
ठीक है,
सर, मतलब हम
प्लीज
लेट देख
प्लीज
रहे हैं।
प्लीज प्लीज म्यूट। शिवम,
यस सर।
बताइए क्या समझा आपने?
सर कि पहले से सिंगल सिंगल लेजर पर फायर होगी, उसके बाद जब वो रिसीव होगी उसी के बाद सेकंड लेजर पर फायर कर सकते हैं। लिमिटेशन है सर उसमें सिंगल पल्स।
गुड। सो ये जो टाइम मैंने कैलकुलेट किया है 2h by c, व्हाट इट इज?
हाँ सर, ये सर सर टाइम है सर फर्स्ट सिंगल पल्स का सर, जो फर्स्ट वाली सर आपने फायर करी उसका।
ये विच टाइम इट इज 2h by c?
सर मिनिमम टाइम पीरियड सर।
नहीं, 2h time, could you tell me in the context of this figure for which process this 2hc by calculated for pulse t1? Just explain about it.
सर कि जो सर ओरिजिन है लेजर का, उससे सर जब वो पार्टिकल से सर फॉरवर्ड टू
नहीं,
बैकवर्ड जाती है।
just start with the pulse t1. What happens with pulse t1 at origin O, that is laser transmitter? It emanates, it is transmitted from there, then what happens?
Then sir it is strike to the object sir, with a speed of
with the speed of light, it strikes with
yes sir.
point P. Then what happened?
Then sir it reflect backward to the
Reflect. It is reflected back to the receiver and it is further sent. So how much time will be needed for that?
Sir, 2h by c, sir.
Correct. So that is a minimum time 2h by c is required. Okay. So let's say remove this minimum. It is actual time 2h by c that will be needed. Okay. And this is the time. So once, let's say at time t is equal to 0, the beam is fired from origin O. Okay. At t is equal to 0, it is fired, and after t is equal to 2h by c, it is received. Then only the next pulse t2 is fired. So the t time period can be taken as the minimum time period that we'll say is equal to 2h by c. Okay. And now this governed, this we have already derived this the relation between time period and pulse firing rate. So this f PFR is equal to 1 by t. And when we'll take t minimum, okay, so this PFR become maximum. I say this pulse firing rate maximum will be equal to 1 by t minimum. Is it clear to all? Okay. Now we'll replace. This is the equation 3rd. And this is equation 4th. Okay. So substitute equation 3 in 4. What you will get? You will get this if PFR max is equal to C by 2H. Now just see. This PFR is inversely related with the flying height. It means there is a trade-off. If you increase this height h, just see very carefully. If you increase this height h, this gap will increase. Why this gap will increase? Because this pulse firing rate will decrease. Okay. So when you increase the flying height, in 1 second, how many laser beams are fired there? That value decreases. Okay. And finally, that lead to the increase in gap between two adjacent laser footprint. It means the point density, quality of data will decrease. How it is affected, how this distance increases, will derive an equation for that later on. Okay, but here you can just establish a kind of relationship between the quality of data, dependency on pulse firing rate, dependency on flying height. Okay, later on what happens? Yeah.
Sir, means if we decrease the flying height, flying height, then the quality of data will be decreased. Isn't it so, sir?
Increase, no? No.
It will increase.
Listen carefully. Listen carefully what I told. If you, all of you, please listen. If you increase flying height h, you can see what I'm writing on the screen. Hello?
Yes, sir, I can see.
So this h increase, what will happen? It is inversely proportional. This will decrease, fine.
Yes, sir.
When this will decrease, then in this gap will increase. If you decrease the pulse firing rate, now then this gap between two laser pulse will increase.
Yes, sir.
Using this relationship, if you're decreasing this, then T increases. T increases means gap between two successive pulse will increase. And then this will further lead to increase in gap between two adjacent laser footprint. When this gap will increase means data density will decrease, no?
Yes, sir.
In one line, less points are hitting on the ground. So if data density will decrease means quality of data will decrease. You can't get a dense point, so you can't actually geometrically represent that object. Is it clear now?
Yes, sir.
नहीं अभी कंफ्यूजन हो तो बताओ. I will repeat once more.
नहीं सर, वो समझ गया सर, वो ध्यान नहीं दिया था, एक पॉइंट छूट गया था उसी वजह से सर। मींस कि अगर जितने ज्यादा पल्स फायरिंग होगी उतनी ज्यादा क्वालिटी डेटा की बढ़ेगी।
हाँ, reason is that ना, see, if you fire the beam at at a fast rate, so this time period will less. In that case, what will happen na? This beam, then next beam, very frequently the beams are fired. This is meaning of high pulse firing rate.
Yes, sir.
So when the time gap between two beams decreases, na, so they are hitting the ground closely.
Yes, sir.
Okay. So fine. So take your time, all of you. Just there is a 5-minute gap, and recall it once more. The entire discussion which we have done. Okay, so let me know. Is it clear to all? Fine. So this was the single pulse limitation in the first version of LiDAR sensor. Okay. After that, internal electronics improved, and after that, the sensor had capability to identify more number of pulses before receiving the return of the first pulse. And then technology is shifted to the multi-pulse identification. Okay. So in multi-pulse identification, let's say sensor has capability to fire 4 pulses all together. This n is equal to 4. So let's say this T1, T2, T3, and T4. 4 pulses are fired in one go before receiving the return of T1. So T1, T2, T3, T4, they are fired. Then after that, a return of T1 is received at the receiver. So the sensor has capability to identify 4 pulses before receiving the return from pulse T1. Okay. So in that case, what will be the T minimum? So generalized formula can be written over here, and that generalized formula is T minimum in that case if sensor has capability to if sensor is equipped with a multi-pulse identification, then T minimum in that case is equal to 2H divided by capital N into C. Okay, so this will decrease, and in that case, what will happen? P, this pulse firing rate maximum is equal to NC divided by 2H. So ultimately, it's n time it is multiplied. Okay, if n is equal to 4, then in case of multi-pulse identification, just see that it is multiplied by the factor. If 2 pulses can be identified before can be fired before receiving the echo of the first pulse, then it will be doubled. Okay. In case of 4, it will be 4 times. In case of n, it is n times. Okay. So in multi-pulse concept, the limitation with respect to the height is further overcome, okay, by incorporating this multi-pulse concept. So we'll see that how this technology evolved in beginning, and okay. So this is a general specification of one of the airborne LiDAR sensor, that is Toposis second. Sensor type, just see the parameters. These are the important parameters, and we have been doing our discussion with reference to these parameters. Okay, to on the basis of quality of data that we obtain. So sensor type, it's a pulsed fiber scanner. Okay, so this pulse laser beam is being used. The range is less than 1,600 meter. So the maximum range that can be covered is 1.6 kilometer. The wavelength 1.55 micrometer. It is in near infrared band. The pulse length, the TP we are talking about, it is 5 nanosecond. Scan frequency, the rate at which the mirror rotate. Okay, we have already discussed in case of terrestrial laser scanning, like laser source and mirror rotates. So in a vertical plane, laser beams are fired. So what is the speed of rotation of mirror? Okay. So how many scan lines we are covering in 1 second is equal to this scan frequency. Pulse repetition rate, actually it's a pulse firing rate. It's 83 kilohertz. Resolution of distance measurements, 0.02 meter. That is fine. Field of view, we have already discussed that. It's a 14 degree. Okay. And if the field of view is 14 degree, then swath at the ground is equal to 2h tan theta by 2. If you see that in case h is equal to maximum 1.6 kilometer, so 2h 3.2 kilometer, tan theta by 2, tan 7 degree. So you will get a swath at a maximum range 390 meter. Average measurement density. Here it is like what is how many laser footprints per meter square by using these parameters. So it is 3 measurement per meter square. Now, with respect to the time frame, starting from 1993, you can see that it is the technology, how that with respect to the change in technology, how the internal parameters are improved. As you
Sir?
see in, yeah.
Sir, in the last slide, there was a pulse length. Means, is it a time period? 5
No,
nanoseconds?
it's not time period. It's length is TP now 50% level. If you see one pulse, so peak is AP, we call a peak amplitude, and
Yes,
50% level, like rising edge where is a 50% and falling edge 50%. That time gap is called as pulse length.
okay, sir. Okay. Thank you, sir.
Got it? Okay.
Yeah.
So this is the view of this sensor, and it is manufactured by Optic. Optic is a company, and ALTM. ALTM is a model. Okay. So this is airborne laser scanner system. And just see. If you see this, the first row talks about type of sensor in terms of single pulse limitation, the single pulse identification, and multi-pulse. So in the beginning, it profilers, then scan single pulse, then scan multi-pulse. And there is a relationship between frequency and height. As I have already derived a relationship between pulse firing rate and height in case of single pulse limitation as well as the multi-pulse facility in the scanner. Okay. 1993, this is the first model came into the market. This is ALTM prototype, and it was flown at height of 1 kilometer. So at 1 kilometer, the pulse firing rate was 2 kilohertz. Now, after in 1998, this model at 2 kilometer, the 10 kilohertz. While in 2001, this range further improved. Okay, as you see that in 1999, this technology became matured. Okay, for the use at a commercial scale. So 2001, the maximum range at which this target point can be captured is up to 3 kilometer, and 33 kilohertz this pulse firing rate was obtained. 2002, again at 2 kilometer improved, it is 50 kilohertz. Then if you see 2006 and 2006, then ALTM enhanced this 3100 EA, that is with enhanced accuracy, and ALTM Gemini. Now 2006, this multi-pulse recognition concepts evolved. Okay, and the internal this transmitter and receiver technology improved so that like multiple pulses can be fired. And as you see that, like if you see in 2006, at 3 kilometer, the 50 kilohertz from the bottom, 4 kilometer, 3 kilometer, these are the distances. At 3 kilometer, you can say that 50 kilohertz was the pulse firing rate. Okay. And if you go back to the 2001, in case of ALTM 3033, at the same 3 kilometer, the pulse firing rate was obtained only 33 kilohertz. So nearly it was doubled in 2006 using the advanced sensor technology. Fine. And these are the key factors which are combined together while doing the analysis. And these are the sensors parameter. Okay. And they finally gives us idea about the quality of data that we obtain. So whether that sensor is its altitude limit, obviously this single and multi-pulse concept limit the flying height. Okay. Then what is the operating altitude? What is the pulse firing rate? At what rate we are generating the laser pulse? Then scan pattern and point distribution. If you recall in one of our discussion, I talk about this rotating mirror and oscillating mirror. Though we'll have discussion on this. So that type of mirror determine what is a scanning pattern, like in what fashion these laser footprints are hitting the ground. Then again, we have a scan field of view, that is theta we talk about, and scanner frequency. Scanner frequency means scan frequency. And these parameters are already listed over here, if you see. Okay, so these are the 6 key factors which govern the entire operation. And as you see, they are depicted over here. So AGL stands for above ground level. The aircraft is flying at height of 4 kilometer. And these parameters are shown, like at 20 degree off nadir, the slant range become 4,257 meter. Okay. Now here it is summarized, the single pulse limitation that we have already discussed. So it's a timing limit. The time pulse takes to hit the ground and return back. So next pulse only sent after previous pulse returns, a hardwired limitation. Because for those models, okay, there was not an internal mechanism to identify, like if let's say this is the return, then it belongs to which pulse. If let's say you are firing multiple pulses at a time, so the internal receiver unit can't identify the return which is coming back. It is from which fired laser beam. So that was the reason why that sensor receiver transmitter doesn't fire the next pulse till receiver received the return of the first pulse. So one numerical is shown over here. Let's say the time period between 2 pulses are 10 nanosecond, and the beam is fired at a rate of 100 kilohertz. So 10 nanosecond, within this time, obviously this total distance will be covered 3 kilometer, multiplied 10 into speed of light. So 10 nanosecond into c. So this time, the gap between the time period t is equal to 10 nanosecond. So within 10 nanosecond, 3 kilometer distance is covered. It's a two-way, forward and backward. It means 1.5 kilometer altitude can be maintained. Okay. So if you want to generate a laser beam, if your sensor is generating laser beam at 100 kilohertz, okay, it means 1 by f, 1 by 100 kilohertz will be 10 nanosecond, its time period. Within this time, 3 kilometer distance is traveled, and half of it will be the limitation for the altitude. It means you can't fly your aircraft beyond 1.5 kilometer. And even if you incorporate some losses, so it will further reduce to 1.1 kilometer. Okay, so at 100 kilohertz, 1.1 kilometer is the maximum height at which you can fly your aircraft. Okay. So this operating envelope overall is bounded by altitude, laser pulse rate, and scan angle. So if you want to maximize one, you need to compromise other. So there is trade-off. As we have already seen that this pulse firing rate is inversely proportional to the altitude. PFR is inversely proportional to H. H is a flying altitude. So if you want to improve one, if you want to increase the flying height, okay, so you need to compromise in terms of laser pulse rate. Okay, so there this multi-pulse significantly alters this envelope. It means this bounding. So this is a conceptual description of single pulse versus multi-pulse. So as you see that the two successive laser pulses are plotted over here in the first case. And this T naught, before firing the next beam, there should be a return. So delta T, it gives like what is time taken by a laser pulse from transmission to reception. So this range. And just see in case of multi-pulse, the return from the pulse first is after the firing the second beam. Okay. And this is the plot versus it's a hyperbola. It will be as its pulse firing rate is inversely proportional to the AGL, above ground level, that is H. So you can see that the maximum pulse firing rate that can be generated, how it varies with respect to maximum H. That is described over here as a above ground level height. Okay. But in case of ALTM Gemini, you can say that typical, if you see ALTM 3100, ALTM 3100 has a single pulse limitation, while ALTM Gemini doesn't has this single pulse limitation, though it was capable of multi-pulse concept, this multi-pulse recognition. So this is reason why even you can obtain high pulse firing rate at the same AGL. So in case of multi-pulse concept that was inbuilt with the Gemini version of ALTM. So this eliminated hardwire limit by redesign of electronics. New timing interval meter. It means that new timing interval meter has capability to identify like from which transmitted pulse the return is coming without interfering with the successive fired laser pulse. Okay, so it is optimized light detection circuitry, better differentiation of return pulses. Okay, and this has a capability to fire two pulses at the same time. It means first beam is fired, that sensor doesn't wait for the return of that beam, it fires the second. After that, it gets the return of first pulse. Okay. And again, this is the relationship between the maximum altitude and pulse firing rate. That is called over here this pulse repetition frequency. Okay. So you can see that at on the independent axis, the frequencies are plotted 33 kilohertz, 50 kilohertz, 70 and 100. If you see this 100 kilohertz in conventional LiDAR, which has a single pulse limitation, the maximum flying altitude could be 1 kilometer. While in case of LTM Gemini, it is double 2 kilometer. Why it is so? Because the two pulses can be fired. N is equal to 2 over here. If you recall that formula we derived, so N is equal to 2 over here. So this flying altitude will be doubled. So this is the reason why it is shifted from 1 kilometer to 2 kilometer. And these are certain practical implications. At this stage, discussion is not needed. Okay. Now the query is flying higher is better? What happens if you fly, you do scanning at higher altitude? Can you think about it, and could you be involved with me in discussion? I'm giving you 5 minutes time. Try to think about it, like when we fly at high altitude, is it better? If it is not, then why? Take your time, 5 minutes. Think about it, then we'll Okay, so we will start discussing about what is the effect of flying height. If we are flying higher, is it better? So can you tell me some points on this?
Sir, on the basis of the equation which we derived, I can say that if we are flying high above better adequate height, then there will be less accuracy for the point data collection. And if the point data collection are less accurate, then we'll have to fly again and again and take the data. Like sir, if there is situation like tropical rainforest areas where that forests are plants are trees are very high, at that position we cannot have accurate data because of the height variation from the ground level. From those places we have to fly again and again to get the accurate and overlapping data. Yes, Master.
Okay, okay, good. So see, first of all, we need to see all the equations where height has the role. Okay. So if you see that the footprint size df, that we determine the transmitted dt plus 2h tan gamma by 2. Okay. So there we see that if you increase height h, then further df increases. So footprint size will increase. So ultimately, we have a kind of limitation in terms of reducing the coordinate accuracy in x and y. If your footprint size increases, df will increase, then error will be added. Fine. Now, this is one limitation that we can see. In
Sir,
case of
quality of data, sir, second point हो सकता है सर as height of light increases, pulse firing rate will be decrease, and this leads to less density, and as a result we get less quality of data, sir.
that is correct. Yeah. So if your sensor has a single pulse limitation, yeah, even we have the facility of multiples in both cases. Even if we have a facility of multiples, so we have derived formula this pulse firing rate if PFR max. What it was? It was n times C by 2h. Was it the formula?
Yes, sir.
This one, okay. NC by 2h. Again, just see, if you increase the flying height, okay, then PFR will decrease. When PFR will decrease, this gap between two laser footprint will further decrease. So overall,
Sir,
what
if
will
you are
happen?
displaying, sir. Sir, are you writing anything, sir?
Yeah, yeah.
Sir, it is not being displayed on this side, sir.
Is it for all of you?
Yes, sir.
Yes, sir.
Sir, only that
Yeah.
presentation part showing, and double tap to add title, double tap to add
Okay,
text.
okay.
This
Let me again share that slide. Okay. Yeah, Sumit, first of all, thanks for pointing out this. Okay, I hope now you can see the shared screen.
yes, sir.
Okay, so just see that the formula DF, the first one, that is footprint diameter, is equal to DT, aperture diameter of laser transmitter, plus 2h tan gamma by 2. Okay, height increases, then DF will increase. If the footprint diameter will increase, it will further lead to error in x and y. Okay. Now the second, we have a single pulse limitation, a multi-pulse, if the sensor is equipped with a multi-pulse technology. Then multi-pulse, we are talking about number of pulses which can be fired without receiving the return from the pulse. If it is n, so pulse firing rate max nc by 2h. Again, if you increase height h, then what will happen? This pulse firing rate will decrease. And if it will decrease, this gap will increase. So ultimately what happened? Decreasing AFR, the point density, the density, we can say data density will decrease. So ultimately, in terms of data quality, how in a detailed representation the object is object points from the object are required, so that will further reduce. So at low data density, there is not a detailed geometrical representation of object. Okay. So in both cases, flying higher is not a kind of pro, it's a disadvantage. Do we have any advantage of flying high? Yes, that we can see over here. The swath is called as, let's say this is the trajectory aircraft is flying. Let's say somewhere if it is located, this is the field of view. Okay, this is the FOV, and this total distance, if it is a slant, we can see it, just if we consider it perpendicular. So this is called as swath. So swath means width of the area strip that is covered in one flight line. So this direction is called as flight line direction. Okay, and this is called as scan line. These terminologies you need to remember. So the flight line direction, scan line direction, this length, width of the area strip that is covered in one flight line is called as swath. How this swath is calculated and how it is related with the this sensors parameter. So if you see over here, somewhere here we have our origin of a laser transmitter. It is this laser sensor is inbuilt with a flying aircraft. And this is the maximum FOV, field of view. And aircraft is flying at height h. So what is the total distance A and B? So distance A and B, it is called as swath. Okay, and it is equal to 2h tan FOV divided by 2. Okay, it's G. Tan FOV divided by 2 is equal to this distance divided by this. Okay, so this distance is equal to h into tan FOV, and this is 2 times. If you add it, to DAB is equal to 2 times of this distance. It becomes 2h tan FOV divided by 2. Now, if you increase height over here, then what happens? This DAB, the swath will increase. So if you are flying higher, the larger area is covered in one flight line. Why it is so? Because this width will increase. It means the time of operation is less compared to flying at low height. So let's say if the 500 kilometer square area is given, and if you want to do the laser scanning, airborne laser scanning to get a 3D point cloud, so it can be done in less time if your flying height is more compared to if you're flying at lower altitude. So ultimately, the budget for that survey, that price will drop. So at low budget, because if your flight line will be more, more flight line is required to cover an area. It means there will be the requirement of more fuel to fly the aircraft. So ultimately, the cost of data acquisition will increase in that way. So cost of the project will decrease when you are flying at higher altitude. This is the benefit, but so it's a cost benefit analysis. Price will drop due to larger swath, less flight lines are required. Okay. So at low cost, the airborne laser scanning can be done, but at the same time, you are compromising with the data quality. So we can say that the cost and data quality are indirectly related, inversely related. If you want a high quality data, you need to pay more amount for that. The cost of the survey will increase once the data quality will, the required data quality will increase. Okay. So these two equations talks about at higher altitude, the quality are decreasing. In the second case, quality is decreasing in terms of data density, while in first case, quality is decreasing in terms of error in XY. Okay, even Z, the larger distance has to be traveled by laser beam. Okay, so there will be error in Z as well at larger distance. So in X, Y, and Z, error will increase from the higher altitude. Data density will decrease, but at the same time, that survey can be performed at a lower cost. So I hope it is clear now. So we have justified that. Is it better flying high? Yeah, it is better in terms of cost of the survey, but it is not preferred if you want very high quality data. Then in that case, you should prefer to fly the aircraft at lower altitude. So is flying higher is better? We have discussed about it. Is wider scanning better? So this I'm leaving to you, up to you, that I expect you to go through this to understand what should be the response. Is wider scanning better? It means if we increase the field of view, FOV, so is it better? Or it should not be preferred? So some points are written over here. On the basis of these points, I expect you to conclude this, whether it is yes or no. Now, this is a description. What is the effect of various parameters on the accuracy assessment? So FOV and elevation error. Just see that if you increase the field of view, then what is happening? The error will at off nadir positions. Okay, at off nadir positions, the vertical error will be high compared to the nadir position. Now the third combination, flying higher, scanning wider. In both cases, you can drop the price, this project budget. Okay, but are they better choice for the quality data in terms of data density and accuracy? So I expect you to do the analysis. Points are given over here, and we have already discussed the enough background for this. And even I'm going to give these two analyses, like flying higher better, scanning wider better or not. In the first case, scanning wider is better or not, as a homework, okay, as a kind of assignment. Now finally, the accuracy consideration. Just see that if you are increasing the above ground level, this flying height, at the same time horizontal accuracy is it's a decreasing. Okay, horizontal accuracy is decreasing when you are increasing the flying height, and it is experiment is performed and the variation is plotted over here. So now in today's session, we have seen that what is the effect of laser footprint diameter on the accuracy, or why we can't perform laser scanning in radio band. Then we have seen that what are the relationship between pulse firing rate and height h, that is we call above ground level flying height, single pulse limitation, multi-pulse concepts, and then mathematical derivation, like what should be the maximum pulse firing rate that can be obtained in case of multi-pulse concept. If we have a option there to fire n number of pulses before receiving the return from the first, so then what is a numerical what is a formula to calculate the pulse firing rate? Okay, so please let me know if there is any doubt.